The National Electrical Code, or NEC, dictates specific requirements for grounding and bonding at electrical systems, particularly concerning the relationship between the utility transformer and the main disconnect at a building or service entrance. Understanding these requirements is crucial for ensuring safety and compliance with electrical standards. Key sections to consider are NEC 250.24 and 250.24 bone. NEC 250.24 addresses the connection of the grounding electrode conductor, or GEC, to the service equipment. This section stipulates that the grounding electrode conductor must be connected to the equipment grounding terminal of the service equipment. This requirement ensures a direct path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. However, the code includes an exception. The grounding electrode conductor connection is not required at the service equipment if the grounded conductor, typically the neutral, is solidly grounded at the transformer or other point of connection to the system. This exception is particularly relevant when dealing with utility-owned transformers that supply power to buildings. If the utility grounds the neutral conductor at the transformer, then an additional bond between the neutral and ground at the main disconnect may create undesirable circulating currents and is generally not permitted. NEC 250.24 bone further clarifies the grounding system by stating that the grounding electrode conductor must be connected to the grounding electrode at one point only. This is a crucial requirement to prevent the creation of parallel paths for neutral current, which can lead to elevated ground currents, electromagnetic interference, and potentially hazardous conditions. The intent is to establish a single, defined grounding point for the entire electrical system. The explanation behind these code requirements lies in the desire to create a safe and effective grounding system that minimizes the risk of electrical shock and fire. When the utility company solidly grounds the neutral at the transformer, they establish a low impedance path for fault current to return to the source. This grounding ensures that any fault current will quickly trip a breaker or fuse, de-energizing the circuit and preventing a prolonged hazardous condition. In such cases, bonding the neutral and ground again at the main disconnect can create multiple paths for neutral current, which can lead to problems. However, if the utility company does not solidly ground the neutral at the transformer, then it becomes necessary to bond the neutral and ground at the main disconnect. This bonding ensures that a proper grounding path exists within the building's electrical system, providing a safe path for fault current to return to the source. This scenario is less common with modern utility systems, but it may exist in older installations or in specific circumstances. The procedure for determining whether to bond the neutral and ground at the main disconnect involves verifying the utility's grounding practices at the transformer. Here's a step-by-step approach. Firstly, determine if the utility company solidly grounds the neutral at the transformer. This is the most crucial step. Secondly, contact the utility company directly. They can provide documentation or verbal confirmation of their grounding practices. Thirdly, examine the transformer connections, if possible and safe to do so. Look for a visible grounding connection from the neutral conductor to a grounding electrode, such as a ground rod or the metallic enclosure of the transformer. However, this visual inspection should only be performed by qualified personnel. If the utility's practice is confirmed where the neutral is solidly grounded at the transformer, then do not bond the neutral and ground at the main disconnect. This is the general rule for most modern electrical systems served by utility-owned transformers. The grounding electrode conductor should still be connected to the ground bar at the main disconnect, but the neutral and ground bars should remain isolated from each other. Conversely, if the utility does not solidly ground the neutral at the transformer, then bond the neutral and ground at the main disconnect. This creates the necessary grounding path within the building's electrical system. The grounding electrode conductor should be connected to the neutral bar, which is then bonded to the ground bar. In conclusion, the decision of whether or not to bond the ground and neutral at the main disconnect hinges on the utility company's grounding practices at the transformer. Always verify this information with the utility before making any connections. Failing to follow the correct grounding procedures can result in unsafe conditions and code violations. Now let's dive deeper into the specifics of grounding and bonding and how they relate to electrical safety. Grounding and bonding are two distinct but interconnected concepts in electrical systems. Grounding refers to connecting an electrical circuit or equipment to the earth, establishing a zero-voltage reference point. This connection provides a path for fault current to flow back to the source, allowing overcurrent protective devices to operate. Bonding, on the other hand, refers to the connection of metallic parts of an electrical system to create an electrically conductive path. This path ensures that all metallic parts are at the same electrical potential, minimizing the risk of electric shock. The NEC provides detailed guidelines for grounding and bonding to ensure electrical safety. Proper grounding and bonding practices are essential for protecting people and equipment from electrical hazards. There are several types of grounding systems used in electrical installations, including solidly grounded systems, impedance grounded systems, and ungrounded systems. Solidly grounded systems are the most common type, where the neutral conductor is directly connected to the earth. This type of system provides a low impedance path for fault current, allowing overcurrent protective devices to quickly clear faults. Impedance grounded systems use a resistor or reactor to limit the amount of fault current that can flow to the earth. This type of system is often used in industrial applications where high fault currents can cause damage to equipment. Ungrounded systems do not have a direct connection to the earth. In this type of system, a fault to ground will not immediately trip a breaker or fuse. Instead, the system will continue to operate with one phase faulted to ground. Ungrounded systems are typically used in applications where temporary interruption of power is not acceptable, such as in hospitals or critical industrial processes. The grounding electrode system is a critical component of the overall grounding system. It consists of one or more grounding electrodes that are connected to the grounding electrode conductor. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the requirements for the size and installation of grounding electrodes. The grounding electrode conductor, or GEC, connects the grounding electrode to the service equipment. The GEC must be sized according to NEC table 250.26, which is based on the size of the service entrance conductors. The GEC must be installed in a manner that protects it from physical damage. Bonding is also an essential part of electrical safety. Bonding ensures that all metallic parts of an electrical system are at the same electrical potential. This minimizes the risk of electric shock if a person comes into contact with two different metallic parts that are at different voltages. The NEC requires bonding of all metallic parts that are likely to become energized, including metal conduits, metal enclosures, and metal equipment frames. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metallic parts together. The size of the bonding jumpers is determined by NEC table 250.102 cone, which is based on the size of the circuit conductors. In addition to bonding metallic parts, the NEC also requires bonding of non-current carrying metal parts that are likely to become energized. This includes items such as metal fences, metal siding, and metal roofing. Bonding these non-current carrying metal parts helps to prevent electric shock hazards. The equipment grounding conductor, or EC, is used to connect the metallic parts of equipment to the grounding system. The EGC provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to operate. The EGC can be a wire, a metal conduit, or other approved means. The size of the EGC is determined by NEC table 250.122, which is based on the size of the circuit conductors. Ground-fault circuit interrupters, or GFCIs, are another important safety device used in electrical systems. GFCIs are designed to detect ground faults, which occur when current leaks from a circuit to ground. When a GFCI detects a ground fault, it quickly trips the circuit, preventing electric shock. GFCIs are required in many locations, including bathrooms, kitchens, and outdoor areas. The NEC specifies the requirements for the installation of GFCIs. Arc fault circuit interrupters, or FCIs, are another type of safety device that is becoming increasingly common in electrical systems. SIs are designed to detect arc faults, which are dangerous electrical arcs that can cause fires. When an SI detects an arc fault, it quickly trips the circuit, preventing a fire. SIs are required in many locations, including bedrooms and living rooms. The NEC specifies the requirements for the installation of SIs. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other events. SPD divert the surge current to ground, preventing it from damaging sensitive electronic equipment. The NEC specifies the requirements for the installation of SPD. In addition to the NEC, there are other standards and regulations that govern electrical safety, including those from organizations such as the Institute of Electrical and Electronics Engineers, or IE, and the National Fire Protection Association, or NFPA. These standards provide detailed guidance on various aspects of electrical safety, including grounding, bonding, and overcurrent protection. It is important for electrical professionals to stay up to date on the latest codes and standards to ensure that they are providing safe and compliant electrical installations. Proper grounding and bonding are essential for electrical safety. By following the NEC and other relevant standards, electrical professionals can help to protect people and equipment from electrical hazards. Understanding the principles of grounding and bonding is critical for anyone working with electrical systems. Now let's delve into the practical applications of these concepts, particularly concerning the scenario where the utility transformer's grounding configuration impacts the bonding requirements at the main disconnect. Imagine a typical residential service entrance. The utility company provides power to the home via a transformer, which is typically located either on a pole or on a pad near the property. The transformer steps down the high voltage electricity from the utility's distribution system to the lower voltage used in homes, typically 120/240 volts. The utility company is responsible for grounding the neutral conductor at the transformer. This grounding is typically achieved by connecting the neutral conductor to a ground rod or other grounding electrode at the transformer location. This establishes a low impedance path for fault current to return to the source. When the utility grounds the neutral at the transformer, it is generally not necessary to bond the neutral and ground at the main disconnect in the home. The main disconnect is the point where the electrical service enters the home and where the main circuit breaker or fuse is located. The grounding electrode conductor from the home's grounding electrode system should be connected to the ground bar at the main disconnect. The neutral and ground bar should remain isolated from each other. This configuration prevents multiple paths for neutral current and ensures that fault current will flow back to the source through the utility's grounding system. However, there are situations where the utility may not ground the neutral at the transformer. This is less common in modern systems, but it can occur in older installations or in specific circumstances. In these cases, it is necessary to bond the neutral and ground at the main disconnect. This bonding creates a grounding path within the home's electrical system, providing a safe path for fault current to return to the source. The grounding electrode conductor from the home's grounding electrode system should be connected to the neutral bar, which is then bonded to the ground bar. To determine whether the utility grounds the neutral at the transformer, it is best to contact the utility company directly. They can provide information about their grounding practices and whether it is necessary to bond the neutral and ground at the main disconnect. In addition to contacting the utility company, it may also be possible to visually inspect the transformer connections if it is safe to do so. Look for a grounding connection from the neutral conductor to a grounding electrode at the transformer location. However, this inspection should only be performed by qualified personnel. It is important to note that the requirements for grounding and bonding can vary depending on the specific electrical system and the applicable codes and standards. It is always best to consult with a qualified electrical professional to ensure that the electrical system is installed and maintained in accordance with the latest requirements. Let's consider some specific examples to illustrate these concepts further. Suppose a homeowner is installing a new subpanel in their garage. The subpanel is fed from the main panel in the house. The homeowner needs to determine whether to bond the neutral and ground at the subpanel. In this case, the utility company grounds the neutral at the transformer. Therefore, it is not necessary to bond the neutral and ground at the subpanel. The grounding electrode conductor from the subpanel should be connected to the ground bar at the subpanel. The neutral and ground bars should remain isolated from each other. Now, suppose a commercial building is served by a separately derived system, such as a generator or an isolation transformer. In this case, the grounding requirements are different. The NEC requires that the neutral of a separately derived system be grounded at the source of the system. This grounding ensures that a low impedance path exists for fault current to return to the source. The grounding electrode conductor from the separately derived system should be connected to the neutral bar at the source of the system. The neutral and ground bars should be bonded together at the source of the system. It is important to understand the specific grounding requirements for each type of electrical system to ensure that it is installed and maintained safely. Grounding and bonding are critical aspects of electrical safety. By following the NEC and other relevant standards, electrical professionals can help to protect people and equipment from electrical hazards. Remember that this information is for educational purposes only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrical professional for any electrical work. Let us also consider how this relates to older buildings and electrical systems, where the grounding and bonding practices may not align with current code requirements. In older buildings, it is common to find electrical systems that were installed before the adoption of modern grounding and bonding standards. These systems may not have a dedicated grounding electrode conductor, or the grounding electrode system may be inadequate. In some cases, the neutral and ground conductors may be bonded together at multiple locations, which can create undesirable circulating currents and increase the risk of electric shock. When working on older electrical systems, it is important to carefully evaluate the existing grounding and bonding practices. If the system does not meet current code requirements, it may be necessary to upgrade the grounding and bonding system to improve electrical safety. This can involve installing a new grounding electrode system, running a dedicated grounding electrode conductor, and separating the neutral and ground conductors at the main disconnect and subpanels. Upgrading the grounding and bonding system in an older building can be a complex and costly undertaking. However, it is essential for ensuring the safety of the occupants and protecting the building from electrical hazards. It is always best to consult with a qualified electrical professional to assess the existing electrical system and determine the best course of action. Furthermore, the type of occupancy also plays a role in the specific grounding and bonding requirements. For example, hospitals and healthcare facilities have more stringent grounding requirements than residential buildings. This is because hospitals and healthcare facilities use sensitive medical equipment that is susceptible to electrical noise and interference. The NEC specifies additional grounding requirements for hospitals and healthcare facilities to ensure the reliable operation of medical equipment and to protect patients from electrical shock hazard. Similarly, industrial facilities may have different grounding requirements than commercial buildings. Industrial facilities often have large electrical loads and complex electrical systems. The NEC specifies additional grounding requirements for industrial facilities to ensure the safe and reliable operation of electrical equipment. The specific grounding and bonding requirements for each type of occupancy are outlined in the NEC and other relevant standards. It is important for electrical professionals to be familiar with these requirements to ensure that they are providing safe and compliant electrical installations. Grounding and bonding are not static concepts. They are constantly evolving as new technologies and materials are developed. The NEC is updated every 3 years to reflect these changes. It is important for electrical professionals to stay up to date on the latest codes and standards to ensure that they are providing safe and compliant electrical installations. Continuing education courses, industry publications, and professional organizations are all valuable resources for staying current on the latest developments in electrical safety. By staying informed and continuously improving their knowledge and skills, electrical professionals can provide the highest level of safety and service to their clients. Grounding and bonding are fundamental aspects of electrical safety. A thorough understanding of these concepts, along with a commitment to following the NEC and other relevant standards, is essential for all electrical professionals. Let's discuss how to test for proper grounding and bonding. Once an electrical system has been installed or modified, it's crucial to verify that the grounding and bonding are effective. Several tests can be performed to ensure the integrity of the grounding system. Firstly, a ground resistance test measures the resistance of the grounding electrode system. This test is performed using a ground resistance tester, which sends a current through the grounding electrode and measures the voltage drop. The resistance is then calculated using Ohm's law. A low ground resistance indicates a good connection to the earth. The NEC does not specify a maximum ground resistance value for all situations, but a value of 25 ohms or less is generally considered acceptable. Secondly, a ground impedance test measures the impedance of the grounding path. This test is performed using a ground impedance tester, which applies a voltage to the grounding system and measures the resulting current. The impedance is then calculated. A low ground impedance indicates a good path for fault current to flow back to the source. Thirdly, a continuity test verifies that the grounding and bonding conductors are properly connected. This test is performed using a multimeter, which measures the resistance between 2 points. A low resistance indicates a good connection. The continuity test should be performed on all grounding and bonding conductors, including the grounding electrode conductor, the equipment grounding conductor, and the bonding jumpers. Furthermore, a voltage drop test measures the voltage drop across a grounding or bonding conductor when current is flowing through it. This test can help to identify loose connections or undersized conductors. The voltage drop should be minimal. The NEC does not specify a maximum voltage drop for grounding and bonding conductors, but a voltage drop of more than a few volts may indicate a problem. In addition to these tests, a visual inspection should be performed to ensure that all grounding and bonding connections are properly made and that the conductors are in good condition. The visual inspection should include checking for loose connections, corroded conductors, and damaged insulation. Any problems that are identified during the testing or inspection should be corrected immediately. Proper testing and inspection of grounding and bonding systems are essential for ensuring electrical safety. Now let's cover some common mistakes to avoid when installing and maintaining grounding and bonding systems. Firstly, improper sizing of grounding and bonding conductors. The NEC specifies the minimum size requirements for grounding and bonding conductors based on the size of the circuit conductors. Using undersized grounding and bonding conductors can reduce the effectiveness of the grounding system and increase the risk of electrical shock. Secondly, loose or corroded connections. Loose or corroded connections can increase the resistance of the grounding path and reduce its ability to carry fault current. All grounding and bonding connections should be properly tightened and protected from corrosion. Thirdly, improper installation of grounding electrodes. The NEC specifies the requirements for the installation of grounding electrodes, including the depth and spacing of ground rods. Improperly installed grounding electrodes may not provide an adequate connection to the earth. Fourthly, failure to bond metallic parts. The NEC requires bonding of all metallic parts that are likely to become energized. Failure to bond these parts can create a shock hazard. Fifthly, improper grounding of separately derived systems. Separately derived systems, such as generators and isolation transformers, have specific grounding requirements. Improper grounding of these systems can create a safety hazard. Sixthly, mixing aluminum and copper conductors. Aluminum and copper conductors should not be directly connected together, as this can lead to corrosion and a loss of conductivity. If it is necessary to connect aluminum and copper conductors, use a listed connector that is specifically designed for this purpose. Seventh, failure to maintain grounding and bonding systems. Grounding and bonding systems should be periodically inspected and tested to ensure that they are functioning properly. Failure to maintain these systems can lead to a gradual degradation of their performance and an increased risk of electrical hazards. Avoiding these common mistakes is essential for ensuring the safety and reliability of electrical systems. Let's discuss specific scenarios related to grounding and bonding in different types of buildings. In residential buildings, the grounding and bonding requirements are relatively straightforward. The main service panel should have a grounding electrode conductor connected to a grounding electrode system, such as a ground rod or metal water pipe. The neutral and ground bars should be bonded together at the main service panel. All metallic parts that are likely to become energized should be bonded together, including metal conduits, metal enclosures, and metal equipment frames. Ground fault circuit interrupters, or GFCIs, are required in many locations, including bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or FSIs, are required in bedrooms and living rooms. In commercial buildings, the grounding and bonding requirements are more complex. Commercial buildings often have larger electrical loads and more complex electrical systems than residential buildings. The grounding electrode system may need to be more extensive, and additional bonding requirements may apply. Separately derived systems, such as generators and transformers, are common in commercial buildings and require specific grounding and bonding considerations. Surge protective devices, or SPDs, are often used to protect sensitive electronic equipment from voltage surges. In industrial buildings, the grounding and bonding requirements are the most stringent. Industrial buildings often have very large electrical loads and complex electrical systems. The grounding electrode system may need to be very extensive, and additional bonding requirements are often required to minimize the risk of electrical noise and interference. Hazardous locations, such as areas where flammable liquids or gases are present, have additional grounding and bonding requirements to prevent explosions. The specific grounding and bonding requirements for each type of building are outlined in the NEC and other relevant standards. It is important for electrical professionals to be familiar with these requirements to ensure that they are providing safe and compliant electrical installations. Let's consider some advanced grounding and bonding techniques. Firstly, equipotential bonding is a technique used to create a zone of equal electrical potential. This is achieved by bonding all metallic parts together within the zone. Equipotential bonding is often used in areas where sensitive electronic equipment is located, such as computer rooms and control rooms. Secondly, isolated grounding is a technique used to reduce electrical noise and interference. In an isolated grounding system, the grounding conductor is isolated from the metal conduit and other metallic part. Isolated grounding is often used in areas where sensitive electronic equipment is located, such as recording studios and medical facilities. Thirdly, harmonic filtering is a technique used to reduce harmonic currents. Harmonic currents can cause a variety of problems, including overheating of electrical equipment and interference with electronic devices. Harmonic filters are used to reduce the amplitude of harmonic currents. Fourthly, surge suppression is a technique used to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, or other events. Surge suppressors are used to divert the surge current to ground, protecting the equipment from damage. These advanced grounding and bonding techniques can improve the performance and reliability of electrical systems in certain applications. Now, consider the importance of documentation and record keeping for grounding and bonding systems. Proper documentation of grounding and bonding systems is essential for ensuring their long-term safety and reliability. Documentation should include a detailed plan of the grounding system, showing the location of all grounding electrodes, grounding conductors, and bonding jumpers. The documentation should also include the results of any testing or inspections that have been performed. This documentation should be kept in a safe place and should be readily available to electrical professionals who are working on the system. Good record-keeping practices can help to identify potential problems and ensure that the grounding and bonding systems are properly maintained. Furthermore, let's think about the future trends in grounding and bonding. The field of grounding and bonding is constantly evolving as new technologies and materials are developed. Some of the future trends in grounding and bonding include the use of new materials, such as carbon fiber composites, for grounding conductors and bonding jumpers. The development of new grounding techniques, such as solid-state grounding switches, is also underway. The increasing use of smart grid technologies will require new approaches to grounding and bonding to ensure the reliable operation of these systems. Staying abreast of these future trends will be essential for electrical professionals to remain competitive and provide the best possible service to their clients. In summary, grounding and bonding are essential aspects of electrical safety. A thorough understanding of these concepts, along with a commitment to following the NEC and other relevant standards, is critical for all electrical professionals.